Hello everyone, good afternoon. Today we will talk about the group algebra. So to begin with, let G be a finite group. Assume that row I, where I rounds from 1 up to k, are all inequivalent, irreducible complex representations of the group G. We denote the dimension of the Wi, where Wi is the space of the representation rho I by Ni, and the character of rho I by chi I for each I. Now consider any finite dimensional complex representation V rho of G. For each I from 1 up to k, you can define a linear operator Pi on V, which is defined as follows. In one of the earlier classes, we have already seen that each Pi is a projection operator. So if we denote its image by Vi, then Vi happens to be a G invariant subspace of V, and that leads us to the following decomposition of the representation rho, which we commonly refer as the canonical decomposition. Okay. Now we will talk about the ring of endomorphisms of a given representation rho. So by an endomorphism of a representation rho, I mean a linear map from V to V, which is G invariant. Okay, let me repeat. It's a linear map from V to V, which is G invariant. So end rho is defined to be the collection of all linear maps which are G invariant. That is, for every G, this diagram commutes. Please note that though I have not written the word linear here, but all the maps that we will consider here are at least, they have to be linear maps. So therefore I deliberately omitted it. So don't just get confused that we are considering all maps from V to V which are G invariants. I mean, that they are not of my concern. We are only considering linear maps. So don't get confused. Okay. So this is a, you can easily see that this is a ring. So the addition of this ring is the usual addition of linear maps, and the product is the composition of G invariant linear maps, because we know that if two G invariant linear maps are composed, then it will be again a G invariant linear map. So it's a ring. In fact, it's an algebra over C. So let me first tell you what it means. So we will make a definition now, a general definition, of course. So let K be a field. A ring A is said to be an algebra over K if there is a ring homomorphism from K to A such that phi K, that is the image of K under phi, is contained in the center of A. So what is the center of a ring? It's defined in the exactly similar manner to the center of a group. So we consider all elements which commutes with every other element in A with respect to the multiplication operation. So thus every small k in this K under phi K goes inside the center of A. Okay, so let me give you some examples of K algebra where K is a field. So first of all, the one very easy example is K itself. In fact, more generally, Kn. So Kn is of course a ring with respect to component-wise addition and component-wise multiplication. And now you can consider the following homomorphism from K to Kn. So a typical element S goes to the tuple whose all components are equal to X. So this is indeed a homomorphism from K to Kn. And of course, since this is commutative, so everything is the center of K to the power n is itself. So therefore, it's a so therefore it becomes K to the power n becomes an algebra over K. The second example is polynomial algebra. So if you just take finitely many variables, one up, let's level them as x1 up to xn. So kxn is the set of all polynomials of arbitrary degree in the with the coefficients from k and in the variables x1 up to xn. So it's also an algebra over k. The homomorphism that you need is quite trivial here. So an element x in small k, uh, it goes to the constant polynomial x. Okay. Next example is matrix algebra. So you just fix a natural number n and consider a set of all n by square matrices of order n over the coefficient k. So it's an algebra over k. So the homomorphism which makes it an algebra is the following, that each element from field, each alpha in k maps to the scalar matrix alpha times I. Okay, and since we know the scalar matrices commute with every other matrix, so in view of that, this becomes an algebra over k. More generally, suppose you have a vector space V over the field K of any dimension. I don't bother whether the dimension is finite or infinite. Then end V, that is set of all linear maps from V to V, is an algebra over K. First of all, it is quite clear that it's a ring with respect to usual addition of linear maps and composition of linear maps. It's a ring. And the homomorphism from K to NV that makes it an algebra is precisely this. So each alpha in K goes to the map from V to V, which is multiplication by alpha. Okay. Next example, which is of particular interest to our discussion, is given a representation rho of G on a vector space V, assume everything is over C, then end V is that is the if you just recall that this is nothing but the set of all G invariant linear maps from V to V, that is also an algebra. We already seen that it's a ring. In order to see it's an algebra over C, what you have to do is you have to get the homomorphism from C to end row, and which is again quite obvious. Every complex number will be sent to the linear map, which is given by multiplication by that complex number. And since scalar multiplication maps are trivially G invariant, so that makes this NP an algebra over C. Okay. So before we go ahead, let's note something very interesting. So if A is an algebra over K, so again let me remind you that that means a priori A is a ring. But now what I'm going to say is, if the ring A is actually an algebra over K, then A can be made a vector space over K in the following way. So in order to make it a vector space, we need two things: addition and scalar multiplication. Since it's a ring, addition is already there. We have to just, what we have to define as an extra is the scalar multiplication that we define in this way. If we consider element alpha from the field K and element A from A, alpha times A is defined as the phi alpha applied on A. So given alpha in K, phi alpha is a member, phi alpha is a member in A, and with that we are taking the, so phi alpha is a member in A, so we are considering the product of phi alpha and A. Okay. So in view of this, now it follows immediately that for every alpha in K and AB in A, so alpha times AB is same as alpha A times B is same as A times alpha B. So note that this is where we need the we need that the image of phi is contained in the center of A, because alpha AB is nothing but phi alpha into AB, then you're using associative phi alpha AB. Now since it's in the center, so you can write like that, A into phi alpha into B, again using associativity, you get this. So this is where we need that the homomorphism sends K inside the center of the ring A. Okay, let's go ahead. Now we will talk about the decomposition of the ring of endomorphisms. So let T be a G invariant linear map from V to V. Recall that we have the canonical decomposition. Okay. Sorry. So T sends element of V to V. So what we will do now is first we will consider, so for any given v in V, TV is a member in V, we are going to consider the ith component of TV. So formally we will consider the following composition. So composition of T with respect to the projection map Ti. So once we do that, if we denote it by Ti happens to be a G-invariant linear map, of course, because everything, both Pi and T, they are assumed to be G-invariant. So it will be G-invariant linear map from V to Vi. So basically we are not we are just considering the so first we have T, then we are for further we are projecting that onto the ith component. So starting with the vector V, from V we get a TV which is in V, then we look at the ith component of the vector TV. Okay, so the Ti is a map from V to Vi. Now we shall restrict Ti on the subspace Vj. Okay, so let's denote it by Tji. So Tji is a G-invariant linear map from Vj to Vi. Okay, so now the question is, what can we say about this Tji? Okay, the claim is the following, that if I not equal to j, then Tji is 0. Why? Okay, in order to see a map is 0, we will try to see that we will try to show its kernel is the whole Vj. Okay, so okay, let's consider the kernel of this map. Since this is a G-invariant map, so both image and kernel will also be G-invariant subspaces of Vi and Vj respectively. So kernel is a G-invariant subspace of Vj, and we know that from one of the earlier classes that the kernel admits a G-invariant complement. So there is a W prime, a subspace which is G-invariant, such that Vj can be written as the direct sum of kernel and W prime. Now what we are going to do is we are going to apply the first isomorphism theorem that says the quotient by the kernel is isomorphic to the image. Okay, so now since Vj is written as the direct sum, so if we quotient Vj by the kernel, so what we get is isomorphic to W prime. Okay, and so thus W prime is isomorphic to the image of Tji. And remember, since Tj is given to be G-invariant, so the isomorphism that we have got is all that is also a G-invariant isomorphism. So that's what we get. In other words, the representation on the sub-representation on W prime is isomorphic to the sub-representation on the image of Tji. Remember, this is just, again, let me tell you, this is just a standard first isomorphism theorem kind of argument. There we get the isomorphism. But since in addition we have the map to be G-invariant, so thus both the kernel and images will also be G-invariant, and kernel admits a G-invariant complement. So from all these we get that from W prime to the image, you have an isomorphism which is also G-invariant. That gives that the representation on W prime is isomorphic to the representation on the image. Now let's observe that suppose the kernel is not the whole Vj, so therefore W prime will not be trivial, so therefore hence this is not also trivial. So thus we have two non-trivial representations now, and they are isomorphic. Now see one thing, that any irreducible subrepresentation of W prime, since W prime is a subspace of G-invariant subspace of Vj, has to be isomorphic to rho j, right? because Vj, the way Vj has been constructed. This is all what we have seen, that Vj is actually some direct sum of Wj's, and isomorphic to a direct sum of Wj's, and Vi is isomorphic to a direct sum of Wi's. So a sub-representation, so once we have this representation and that representation, any sub-representation of W prime is isomorphic to W is isomorphic to Wj. So thus W prime is, as a representation, isomorphic to some direct sum of Wj, but here it is isomorphic to some direct sum of Wi's, and if I not equal to j, certainly that cannot happen. So the upshot is, if j is not equal to I, then Tji has to be 0. So therefore, if we just have a thorough look, so first what we have done is, starting with a invariant G-invariant linear map T, we first project it onto the ith component and then restricted it to the to Vj. Then we see that if Vj is if j is not equal to I, then that Tji has to be 0. So the upshot is, let me tell you, so each Vi goes exactly inside Vi, because in the image of a vector from Vi by T, this shows that any other jth component must be 0. So the upshot is T of Vi is a subspace of Vi. Okay. So now from here, I leave this to you to convince yourself in the sense that you have to verify the small details that shows the endomorphism ring is actually, this endomorphism algebra is actually the direct sum of these algebras. So rho Vi is nothing but the subrepresentation of rho on the subspace Vi. Again, this is very simple. How we get it? So suppose any t here can be actually, so any t, so this in fact this is, I have written down the isomorphism as well. So if you take any t here, then since any t sends each Vi to Vi, so thus in order to understand, or in order to get t, it's enough to have in our hand what it does with, how it acts on each Vi. And equivalently, suppose I have a G-invariant linear map on each Vi, so their sum is going to be G-invariant linear map on V. So this is what the isomorphism is under consideration, that each t is written as the sum of the restrictions of Vi's. Okay, and one more thing, that this is this isomorphism is an isomorphism between algebras over C. So let me first explain. Let me first tell you what it means. So suppose A and B are two K algebras. So we will say A is isomorphic to B if there is, first of all, a ring homomorphism from A to B. Remember that whenever we are considering, since A and B are K algebras, so a priori both of them are rings. So if you want to talk about between them, so first of all, we need a ring homomorphism from A to B. And then furthermore, since these are algebras, so both of them can be made vector spaces over K. So the ring isomorphism which we are talking about, we also insist that to be a linear map. So again, let me repeat. So I will say to algebras A and B over K are isomorphic if there is a bijective map which is a ring homomorphism, and as well a linear which is a ring isomorphism, and as well a linear isomorphism. Okay, so thus we can see that T goes to this, that we restrict T on each and every Vi. Uh, so this establishes an isomorphism between algebras over C. Okay, let's go ahead. So thus we have this decomposition. The first step towards decomposing the endomorphism, the algebra and endomorphism algebra of a representation row. Okay. So now try to observe that since this is isomorphic, this algebra is isomorphic to the direct sum of these algebras. So in order to understand the structure of this, in order to understand the structure of this, it's enough to understand the structure of these algebras. So, and what about these representations? Remember, rho vi is the direct sum of vi is the direct sum. Vi is the direct sum of wi's. So, thus each of these summands, in each of these summands, the representation which is appearing is actually the copy of the a fixed irreducible representation. So keeping that in mind, we will now try to study the ring of endomorphisms of a representation of the following type, where W lambda is an irreducible representation. Okay. So again, let me repeat. In VI, earlier we saw that end rho is the direct sum of end row VI's, and rho VI is structurally nothing but the direct sum of the same irreducible representation rho I. So therefore, if we can determine in general how the ring of endomorphism of a representation which is direct sum of some fixed irreducible representation, then we will be done. Okay, now let's go ahead. So now let's take a gene variant map from m copies of W to itself. So as earlier, we will define TLKs. Let me just remind you that remind you how it is defined. So first we will project T onto the kth summand here. That will be a gene variant map from this to W, and then we restrict it to the lth summand of the left hand side. So that gives me the restriction map, which is of course that gives me the restriction map, which is of course gene variant. And remember TLK, thus we have obtained is a gene variant linear map from W to W. Since lambda is assumed to be reducible by Schur's lemma, TLK is precisely given by some scalar that's denoted by CLK. Okay. Now it's very easy to see. So each T, suppose you again, let's try to follow it carefully. So any real, if you take any gene variant linear map T, restrict it if you restrict it to any summand here, and then of course take the projection to a projection of that restriction map, which is T alpha k, then it happens to be determined completely by a scalar. Okay. So since T is completely determined when all TLKs are determined, because you see that's what we need to have. We need to know where a typical vector from a summand goes to, and then in order to know where it goes to, we just have to know what its components are. So thus T is completely determined if TLKs are determined and TLKs are given by CLK. Thus what we get is a linear gene variant linear map is uniquely determined by a collection of complex numbers CLK, L and K, both running from 1 up to n. So from here, we obtain an isomorphism of this ring of endomorphisms to the matrix algebra. Okay, so I just leave the details of the painstaking details of checking its isomorphism. I leave the details to you, but this is the idea that we see that the restriction of T on every component, and then if we consider its projection, then what we get is just a scalar by means of Schur's lemma. So T is uniquely determined once we have this collection of complex numbers, and that leads us to the following isomorphism between these algebras. Okay, and as I said that the final and the detailed verification that is indeed an isomorphism between algebra, I leave it to you. Recall that an isomorphism between algebra is a bijective map, which is a ring homomorphism and linear map as well. So I leave this to you. This is a routine checkup. So it's a routine verification. So thus we get that if a representation is the direct sum of some of fixed irreducible representations, let's say m number of summands are being considered, then the ring of endomorphism is nothing but the matrix algebra of the algebra square matrices of order m. So putting this and what we have seen earlier, so if we put these two together, we get that endomorphism ring of representation rho is actually isomorphic to the direct sum of matrix algebras. Okay, yeah, so we get this endomorphism algebra is direct sum of matrix algebras, and where mi is the number of mi is the number of occurrence of the irreducible representation rho I in rho. In other words, this is precisely, in other words, it means that Vi is isomorphic to direct summand of Wi mi times. Okay, so this is the decomposition of the endomorphism algebra. So in particular, suppose if I take rho to be R, which is the notation for the left regular representation of G, then we get endomorphism of left regular representation is isomorphic to this. So this is because we know that in the left regular representation, every reducible representation occurs with multiplicity ni, that is every irreducible representation rho I occurs inside rho ni times, where ni is the dimension of rho I. So thus we get the decomposition of the ring of endomorphisms of the left regular representation. So in the next video we will see how, based on this, we can determine and we can understand the structure of the group algebra. Okay, thank you for your attention.